Hi and welcome back to maths class. Today we are looking at continuous random variables. We've already been looking at discrete random variables, so before we get started, let's just remind ourselves what a random variable is. So see if you can remember. A random variable is a function that assigns a number to each outcome in the sample space. So in a simple example, if I take a coin and I toss it 3 times and I count how many heads I get, then my number x can be defined as the number of heads in 3 tosses of the coin. So x can take 4 different values. It can be 0 or 1 or 2 or 3. That's a discrete random variable. So now we're looking at continuous random variables. So how is that different? Here's an example. I've got a pine forest of 1,000 trees that was planted 10 years ago. So today I'm going to go choose a random tree and measure its height. So the first thing to look at is the fact that I've got height. Okay, if I'm counting heads, clearly I'm either going to have 1 or 2 or 3 or no heads. I'm not going to have 1.5. All right, but when I'm measuring height, then now my values can take on any number in the number line within a certain reasonable domain. Obviously, I'm not going to have a negative height, and there's going to be a maximum limit as well. But within a certain interval, I can then measure any value. So the height of the tree then is my random variable x, and we're going to call it in meters. So what are the possible values for x? So let's remember that now x can take 9 or 10 or 11 meters, but it can also take 9.5. It can take 9.1, it can take 10.0, it can take 10.001, and so on. So what is the probability then if I have an infinite number of values? What's the probability that I get a value of exactly 10? And the surprising answer to that is it's 0. But this is a very theoretical idea, and when we think about that, you need to remember the fact that I'm talking about having a height of precisely 10. And the reason the probability of that is 0 is there are so many other possible values that x can take. There are infinitely many values that the probability of this particular one happening is 0. But that's a kind of meaningless thing for us to ask. We don't really want to know what's the probability that my height is exactly 10 meters. Really, when I get up on my ladder, I'm going to yell down to whoever's taking notes, it's 10.1 or it's 10.2 or it's 10.3. I'm not even interested in measurements in less than 10 centimeters. Okay, I don't want to know if it's 10 meters and 1 centimeter. 10 meters and 10 centimeters is accurate enough for this particular exercise. And that's the case in most things that we measure in real life. If I measure my height, I'm going to tell you how many centimeters. I'm not going to go to the half centimeters because it's not important. So our measurements become kind of discrete just by virtue of the way we measure them. So let's explore that in a little bit more detail then. So first of all, continuous random variables, I've discussed this, can take any value in an interval on the real number line. So there's no gaps in your number line. And the exact value of a single probability cannot be obtained because that's not what we're interested in. So here's an example. I've got a weight of 83 kilos. If I tell you something's 83 kilos, what I'm really saying is it's between 82.5, which is rounded up to 83, and 83.5, which we're not including that endpoint because that would not be rounded down. But everything slightly less than 83.5 is going to get rounded down to 83. So if I now tell you it's 83.1 kilos, you now know that it's between 83.05 and 83.15. If I go a bit more precise and say it's 83.01, then what you really in reality know is it's between 83.005 and 83.015. If I ask the probability that the weight equals 83, then if I mean exactly 83 kilos, then that equals 0. But that's not what I usually really mean. So instead, when I say what's the probability that the weight is 83, what I'm really asking is what is the probability that it's somewhere between 82.5 and 83.5. So here is a histogram, an imaginary histogram that I have collected all these different people's weights, and what I've got there is all that data collected together. So I can see that down here is my 83 exactly, but the shaded column represents all the weights that fall between 82.5 and 83.5. If I want to calculate the probability of the weight being in this interval, that's this probability I'm looking for, then it's going to equal the area of the shaded region divided by the total area. So, I can get the area of this by measuring its width and its height. So its width is 1 and its height, it's not marked. But if I knew the value, then I could calculate this shaded area. And then I would have to add up all the other areas, and I could calculate the probability that my weight is going to fall within this interval. When I say my weight, I mean the weight of the randomly chosen, I think this is people data. Now, if I'm calculating areas of rectangles, this should look familiar to you because we've done calculating areas of rectangles before when we were doing things, but we weren't doing it for probability. So let's imagine going a step further, and instead of having a width of 1, what if my width was 0.1? That means each one of these columns has to get divided into, and I can't draw it accurately, but I've got 10 little columns. So in actual fact, they're not going to all be the same height. Probably this one's going to be a little bit taller, this one a little bit less tall, and then this one will be here and here. And probably these ones will be slightly lower so that they're coming to meet this guy. All right. And then if I make my intervals even narrower again, and then make them even narrower again until my intervals are infinitely narrow, so the width is practically 0, and I have infinitely many of them. Okay, I hope this is familiar to you. We're heading towards areas under the graph. Oh, I didn't mean to do that. What do I need to do? Hang on. So this is what I wanted. And what you can see there is the red line is a smooth curve, which is what this histogram would look like if I made all the rectangles infinitely narrow and then attach them and then got their heights. So in fact, it wouldn't really match up because what would happen is the height of each individual column would be lower because there are fewer values within each column. Right? If I go back to this graph here, each one of these little columns is going to have about 1/10 of the number of data values than I had before. So the heights of the columns will be smaller, but the shape of the graph will stay the same. The peak will still be up here. And that's why when I look at this, I'm happy with lining that red line up there because I've got no values written here anyway. The shape is going to look like this. And you'll notice that each of these goes exactly through the center, right? Through the center like that, okay? This is called, excuse me, this is called my probability density function. And it is a function f of w. But there's a couple of important things I need to point out about this function. Oh, I'm going, okay. So the first thing I need to point out is that f of w is a probability density function, not a probability function. The values of f don't give us probabilities. In fact, the probabilities are found by the area under the curve. So if I take the total area under the curve as being 1, then the area of one interval, like let's say this interval here, divided by 1 will give me the probability of that happening, just as when I took this shaded area and divide it by the total shaded area, that gave me the probability. If I now take this interval in between, let's say in between A and B, here's A and here's B, then because my total area under the curve is 1, that means that this shaded area is going to give me the probability. So the probability is not given by f of w, but by an integral. So let's look at the next thing to explain that further. So a probability density function that has a domain of an interval from c to d has these properties. First of all, f of x is positive. It's greater than or equal to 0 for all values of x in this interval. And that's because my area under the graph has to be positive if my probabilities are going to be positive. Okay, so if it's a probability density function, then it's got these properties. And also the area under the graph is going to be equal to 1. And C to D is my domain. So now I hope that's clear enough for you to read that we say that f is the probability density function of x, remembering that x is my variable. So for example, x might be the heights of the trees. So the probability that my height falls within a particular range is given by the integral over that interval. So if my interval is, let's say, from 9 meters to 10 meters, then a is 9 and b is 10, and then f of x dx. So I find the integral, because the integral is going to give me the area under the curve. So what do I do with all this? Let's have a look. There's my first worked example. Random variable x, and I don't know what x is here. I don't know what it stands for. I'm in really theoretical territory here. Just x has a probability density function with this rule, and it's a piecewise function. So I can see that it has a clearly defined function for x is between 2 and 4, and then when x is outside that interval of 2 to 4, then it simply equals 0. Okay. I need to find a. So what I'm going to use is the fact that I know that if this is a probability density function, then the total area under the graph of f of x dx is going to equal 1. All right. What that also means, because for this part of my graph, my graph equals 0, f of x equals 0. That means it's simply a horizontal line along the x-axis. So there is no area under the graph. So the left-hand side then is going to be equal to the same as the interval from 2 to 4 of this part of the function. That is still going to be equal to 1. Okay, so I just want to show you what that looks like if I do a quick sketch. Okay, so if I look at a times 12 minus 3x, I know that I've got a straight line with a negative gradient, assuming that a is positive. It might not be, but that doesn't matter. I can still do my thinking just with the assumption that a is positive. So what I've got here then is a graph that actually, this part of the graph is not there. I drew my straight line, but then I drew in the points where x is 2 and 4, and I connected those up, and now what I've got is actually a function that looks like this. It equals 0, and then from here I've got an open circle, and this is a closed circle up to here, and now I've got another open circle here because I'm not including, see, these points are not included when x equals 0, but then when f of x equals 0, those endpoints are not included. So the graph goes along the x-axis. So what I'm saying, when I say the area under the graph has to be 1, there's no area here. There's no area here. So I have to write this part. This is my formal definition of a probability density function, that the integral of f of x dx is going to equal 1. That is over the entire domain of f of x, and that's true. But I don't need to add these parts because this bit's going to be 0 and this bit's going to be 0. So an equivalent statement is to say that the interval from 2 up till 4, 2 to 4, of this function here, a times 12 minus 3x dx, is going to equal 1. So now all I need to do is integrate my left-hand side I'm going to leave that constant term a on the outside, and I get 12x minus 3x squared over 2 from 2 to 4, and this is still all equal to 1. This is going to give me an equation that I can solve. I'm basically going to find a, because that's my question, find a, by solving this equation. So let's now substitute. I get 12 fours is 48. X squared is 16 over 2 is 8 times 3 is 24, minus 12 twos is 24, and then minus 3 times 2, which is 6. Okay, 48 minus 24. Minus 24 is 0. Minus negative 6 is positive 6. And then this is still multiplied by a. So I've found, oh, can you guys see that? Not quite. I've been writing equals 1 on the right-hand side. If I just shift over to the left, I've got 6a equals 1. That gives me a equals 1 over 6. Okay, hopefully you can see that. Yes, you can see that. All right, so I've found a. So what I've basically done is I've looked at the fact that I'm told, just going to highlight for you the steps in solving this. I'm told it's a probability density function. Therefore, I know that this has to be true. So I'm using this fact, and then I'm using the fact that the function equals 0 everywhere except here to say that I know that this thing circled in red is the same as this second line of working. I know it equals 1, and now I've got an equation involving a, and I just solve it. Okay. And sorry, I've just realized I need to go back and put some notation in here. This is not an indefinite integral. This is a definite integral, but it's from negative infinity to infinity. So we want to mark that in. In fact, I'm missing that earlier in my notes as well. Just a sec. So let's summarize by looking at the properties of a probability density function. First of all, if I have a function f of x, then it's got to be greater than 0 for all x. We discussed that already. And also the integral of f of x dx from negative infinity to infinity must equal 1. From negative infinity to infinity must equal 1. But if my function is defined in a piecewise way, like the example there, well, that's not an example, that's a general description. If f asterisk x equals a piecewise function f of x over a certain interval from a to b and 0 elsewhere, sorry, I need to shift that, then the integral from a to b of f of x dx equals 1. And that's what we've just done in this example, that we didn't need to calculate the integral from negative infinity to infinity. We just needed to calculate it from a to b. However, sometimes we do have an unbounded domain. That is, especially when it heads towards an asymptote, we can have an area under a curve being equal to 1, even though we don't have a given boundary. We're going from negative infinity or up to positive infinity. So I'm going to stop here, but in the next interval, I'm going to go through an example like that. Sorry, in the next video, I'm going to go through an example like that. All right, that's the end of our first video on continuous random variables.